Hello, we have here a mass tied to a spring which is fixed to the ceiling, let's say. So if I displace this by A and let go, it's going to go into oscillation with amplitude of A, right? Straightforward because it's a free oscillation. So if you displace it by A, it will oscillate with amplitude of A. In this video, we are not interested in free oscillation, we are interested in forced oscillation. So in that case, this end will not be fixed. Instead, it will be a driver. So the driver itself will be oscillating with an amplitude of, let's say, A0. So through the spring, the driver will exert a periodic driving force on, shall I call it the drivee? Alright, so driver and drivee. So the drivee is going to be forced into oscillation. What is the amplitude of this forced oscillation? That depends on the driving frequency, among a few other things, yeah? So this is illustrated by the so-called resonance graph. So on the vertical axis, what's plotted is the amplitude. Whose amplitude? The drivee's amplitude. And on the horizontal axis, what's plotted is the frequency. Again, which frequency? It's the driver's frequency. What the graph shows is that when the driving frequency is too low, when the driving frequency approaches zero, the forced oscillation will have an amplitude of A0, which means when the driver is oscillating at a very low frequency, the drivee will also be oscillating at the same low frequency and at the same amplitude too. Now at the other end of the graph, it's showing that when the driver frequency is too high, then the drivee's amplitude approaches zero, which means when the driver is oscillating like this, very high frequency, then the drivee will also be oscillating at the same high frequency, but with practically zero amplitude. So too low, too high, the amplitude is also not high. So how can we force this guy into a large amplitude oscillation? You got to force it at the resonant frequency. In practice, the resonant frequency is practically the same as the drivee's natural frequency. So there's something beautiful about it, yeah? So when the driver is oscillating at the drivee's natural frequency, then boom, you get resonance. Okay, I'm going to use this applet to illustrate resonance. This applet is written by Walter Pfund. It's a very nice applet. It allows us to set the driver's frequency here. So let's start with a very low driver's frequency of 0.5. Now what is drawn in this graph here in blue is the drivee's displacement or position, and drawn in red is the driver's position or displacement. So let's start the simulation. So you see, initially the drivee is trying to resist, yeah? It is trying to oscillate at its own natural frequency. This is the blue line, yeah? The high frequency part. That's the drivee's natural frequency. But you see, given enough time, the drivee will give up. It will give up trying to do it at his own natural frequency. He's now forced to oscillate at the driver's frequency. And the picture looks like that, huh? This outcome, I think, can be understood quite easily. So basically, the driver is oscillating so slowly that the drivee can keep up with the driver's motion exactly. So when the drivee copies the driver's motion exactly, they have the same amplitude, right? So this explains why on this end of the graph, when the driver frequency is too low, the forced oscillation's amplitude is basically the driver's amplitude. Okay, now let's try a frequency that's too high. So let's set the driving frequency to 10 and let's start the animation. Okay, so this outcome again I think can be understood quite easily. So basically the driver is oscillating so fast that this guy cannot keep up at all. It is oscillating at this guy's frequency, but you know, this guy is pushing down, pulling up, pushing down, pulling up at such a high frequency that before I can react to the push, it has become a pull. Before I can react to the pull, it has become a push already. So the end result is I basically stay put there. So this explains why on this end of the graph here, when the driving frequency is too high, the forced oscillation's amplitude is basically zero. Okay, now let's do it at the resonant frequency, which I know is 3.16. Let's start the simulation. Okay, from the graph you can see the drivee, the forced oscillation's amplitude becoming larger and larger. This is resonance, yeah? Eventually, it will reach a stable amplitude. Let's just give it a bit of time for it to reach a stable amplitude. Yeah, I think that's about it. You can see from the diagram here that something remarkable is happening here. So this guy is pushing down, pulling up, pushing down, pulling up, pushing down. pulling up. Notice it's doing everything at the correct timing. Whenever the driving is on the way down, I will push it down. Whenever it's on the way up, I will pull it up. So I'm applying a force that's always in the same direction as the drive's velocity. You know that when the force and displacement are in the same direction, you do positive work. So what's happening during resonance is you are doing positive work all the time. So the transfer of energy cannot be more efficient than that. That's why at resonance, that's the highest amplitude, the maximum amplitude that can ever be achieved by the force oscillation. Okay, I hope you have a better understanding of resonance now. That's all. Ta-ta!